Right now, the phone in your pocket is pulling off a physical impossibility. It can run complex neural networks and generate human-like text in milliseconds, all on a chip the size of a fingernail. But here is the secret chip makers do not want you to know. That speed is an illusion. Your processor is not actually that fast. To make you think it has to lie, guess the future, and leave your most private data completely exposed. For decades, the tech industry relied on a simple rule. Shrink the transistors, and the chip gets faster. But we have hit an atomic wall. Today, transistors are only a few atoms wide, and we cannot make them any smaller without electrons literally leaking through the barriers. This created a massive problem called the memory wall. While processors have become incredibly fast, the system memory where data is stored remains painfully slow. Every time an AI model needs to run a calculation, the processor spends 90% of its time just sitting there, waiting for data to travel across the motherboard. To bypass this physical speed limit, engineers invented a brilliant logical cheat code called caching. Imagine you're a clerk working at a desk. If you need a document from the main archive down the street, it takes you an hour to get it. That archive is your system memory. To speed things up, you install a small desk drawer right next to you that can hold just 10 documents. That drawer is your cache memory. By keeping the most critical AI data directly on the chip, the processor does not have to wait. It can access the data instantly. But this introduces a massive logistical nightmare. How does the chip know which data to keep in the drawer and which data to leave in the distant warehouse? The chip makers resolve this with a technique called speculative execution. Instead of waiting for you to tell it what to do next, the chip guesses. It acts like a mind reader. If a local AI program contains a branch of logic, the processor does not wait for the decision to be made. It predicts the most likely path and runs the entire calculation ahead of time. If the chip guesses correctly, the calculated data is already sitting in the ultra-fast cache, and the program runs instantly. If the guess is wrong, the chip simply throws away the work and starts over. To the user, it feels like magic. But this is exactly where the trap is sprung. Here is the fatal flaw. When the processor makes a wrong guess, it discards the calculation, but it cannot erase the laws of physics. The data it speculatively fetched still had to pass through the cache. It leaves a physical trace. Imagine our office clerk pulling a secret file from the archive based on a guess, realizing it was the wrong file, and putting it back. Even though the file is gone, the desk drawer is still warm. A competitor walking by can touch the drawer, feel the heat, and instantly know which secret document was just looked at. In the world of silicon, this physical warmth is measured in nanoseconds. This is called a cache side-channel attack, and it is devastating. An attacker does not need to bypass your security firewalls or crack your encryption keys. Instead, they run a simple program that measures how long it takes the processor to access specific pieces of memory. If the access takes 40 nanoseconds, the data was in the cache. If it takes 100 nanoseconds, it was not. By running these precise timing measurements over and over, an attacker can reconstruct the exact secrets that the speculative engine touched, including your master passwords, your cryptographic keys, and the proprietary weights of the local AI models running on your device. The semiconductor industry is now trapped in an impossible trade-off. We can make chips highly secure by turning off speculative execution and completely isolating cache lines. But if we do that, device performance plummets. Some tests show a performance drop of up to 50%. In a market where consumer devices are sold entirely on how many trillions of operations they can perform per second, no chip designer wants to build a secure chip that runs at half the speed of their competitor. Tech giants have tried to deploy software patches to cover these vulnerabilities, but software cannot permanently fix a physical design defect built into the silicon itself. To build a truly secure future, we have to rethink how chips are designed from the ground up. Researchers are now looking at open-source architectures like RISC-V to build hardware-level detection systems that spot timing attacks as they happen. But until these new designs enter the consumer supply chain, every speed boost we enjoy on our local AI devices comes at a hidden price. We have traded the fundamental security of our hardware for the illusion of instant speed, and the ghost inside our silicon is not going away anytime soon.